Welcome to Study Loop.
F, G, and Q are polynomials that satisfy this equation here. For all x's except when Q is 0, and then we'd like to go ahead and show that F equals G for all x. So here, I guess case 1, we should consider, but it's kind of a silly case here. This is if Q is just the 0 polynomial. So let me go ahead and put this bar here. So this says Q is, it's not that Q of x is 0 for some x. It's 0 for every x. So if this is true, then we automatically have F equals G, because we'll never find an example in which F is not equal to G for some x satisfying Q of x not equal to 0, because, and this can't happen because Q is always 0. So in that case, it's vacuously true. There's really nothing to show. Then the second case is Q is only 0 for some x, so for finitely many x's. A polynomial could have only finitely many zeros, so it's either always 0 or only 0 finitely many times. So now if, for example, if Q of A is not equal to 0, then we can use this equation up here, and we have F of A over Q of A, G of A, Q of A. Since Q of A is non-zero, we can just cancel these, and then we see F of A equals G of A. So if A satisfies this equation here at those A values, F equals G. Now suppose that Q of A does equal 0. This is where we'll have to use the continuity, and that's what the hint is suggesting. So F of A, we can write this as a limit as x approaches A of F of x. This is by continuity of F. F is continuous because it's a polynomial. This is given. So then we can write this as the limit as x approaches A of G of x. So this is, of course, when x satisfies this equation here. It can be 0 in the denominator. So again, we have to make this assumption here if we want this last equation. Now using continuity of G, we can write this last expression as G of A using continuity of G. So this is because G is continuous. But here's what we've shown. We've shown for any A, whether Q of A is 0 or not, we always have F equals G. So this shows that F equals G for all x values. And that's our final answer.